still on ODE about the boundary value problem. Yeah. So we have learned before that we have an initial value problem in which we have the condition specified at the same value of the independent variable. Yeah. So when we have the initial value problem as we have before, we have x at x0, which is the initial point. We have the corresponding value of y. For example, y is equals to 1. Now we will look at another ODE in which we use different values of independent variable. Yeah, so usually we can use at extreme points or boundaries of a system. So for example, we have the value of x at 0, in which we have the value of 1, for example, and we have another point in which, for example, we have x is 1. Now the y value, for example, is 4. So we have two different value of independent variable. One is at x equals to 0 and the other at x equals to 1. So this is called the boundary value problem. Because we have a value which bounded the solution. Yeah? We have two value which bounded the solution. Okay, so this is the example of the difference. Yeah, so we can see here we have exactly the same ODE, in which this is the second order ODE. It contains the second derivative and also the first derivative in the equations. The left and the right here is exactly the same equations. But we see here that the treatment is different. On the left, we have the initial value problem, in which we have the auxiliary condition. Yeah, the auxiliary condition is given at the same point, yeah, which is at t equals to 0. Yeah, so if we look at this function, we have x as a function of t. So we have here that t is taken at the same point, which is t0. So what we have here, we have the x value, and we have the gradient of x, yeah, at t equals to 0. So that will be 2.5. So the important thing is to note here is that if we have if we have the ODE, for example, if we have second order ODE, it means that we have two conditions. We need two auxiliary conditions. Yeah. Now we will look at on the right here, we have exactly the same equation, which is this is a second order. Yeah, so when we have the second type here, in which we have two boundary condition, yeah, two boundary conditions here, yeah. The first one here we have t equals to 0, so that the value of x is 1, and at t equals to 2, we have the x value will be 1.5. So we have different value, yeah. We have different value, different point to specify the condition. Yeah, so it means that we have second order ODE. We need two conditions, and these two conditions specified at different points. Yeah, so this is the result. Yeah, if for example we have equations in which in the initial problem, so that we can divide the second order ODE into two first order ODE. Yeah, so that we define it into two first order ODE, so that now we can solve for each of the variables here, which is y1 and y2 here, using initial conditions, so that we have the result for the first equations, and also we have the result for the second equations. So this is the initial value problem. If we have the boundary value problem, it means that we have one equations of the second order ODE, so that we will have one solution in which this will be bounded by two boundary conditions. One is specified at x equals to 0, and the other is specified at x equals to L. So that we will see the example here. Yeah, the example is most common in heat transfer. So if you have learned heat transfer before, so you might have learned this as well. So this is one-dimensional heat conduction in a rod. So for example, we have a rod here and we have the left boundary condition is held at a constant temperature of T1. And the second boundary condition, which is at x equals to L, the temperature is held at T2, so that we will have because this is held at different temperatures, so that we will have a heat conduction. In this case, we have the heat flux from T1 to T2. And we also have the heat flux, the heat transfer to the surrounding, to the ambient temperature, which is TA. So here we sort of have a convections to the surrounding. So this is one of the example for the boundary value problem, in which we have two boundary conditions specified at different point, which is x0 and xl. Now, how to solve this? We have two methods. Yeah, the first one is the shooting method, and the second is the finite difference. So what you might have learned in heat transfer is using the finite difference method. But we will look at the first method here, which is the shooting method first. And this is basically combining the initial value problem to satisfy the second boundary condition in this case. Yeah. So we'll look at here. Say we have 1D heat conduction in a rod, in which we have the governing equation specified here. So this is the conduction, and we have convection. Yeah. And that will be equals to 0. In this case, we don't have the additional source sum. We don't have heat generation, or we don't have the heat sink. Yeah. So that when we have the value specified, yeah, for example, we have the ambient temperature, which is 20 degrees, and we have the length of the rod, which is 10 meter, and we have H accent, which is heat transfer coefficient. So actually we have convection coefficient, and we have K here, which is the conduction coefficient, if you learn in heat transfer. But now we collect all of this value together, so that in general we have heat transfer coefficient, which is denoted by H accent. And we have two boundary conditions. The first one is specified at x0, which is the temperature held at 40 degrees Celsius. And the second, at the right corner, yeah, on the right side, we have at x equals to L, the temperature is held at 200 degrees Celsius. So with this, we can also do the direct integration to solve for the analytical solution, in which this will be the analytical solution. So that if we have the position of x in the rod, we can insert that and we can find the temperature. Okay, so we will see how to solve this. First one, numerically using shooting methods. So what we do in the shooting method is that we will use the initial value problem that we have before, in which we will do marching from one point, from initial point to the other point, so that we have up to XL. So for example, we have the value at x equals to 0. And then we have the value here, which is the target at x equals to L. So when we do marching, for example, you can use any Runge-Kutta method that we have learned before. For example, you can use Euler's method, or you can use the midpoint, or you can use the Hund's method. And then we can find the value at x equals to L. So for example, here we have the value of XL here is too large, or we can say that there is an overshoot. So it means that this not the result that at this point is not satisfying the second boundary condition, which is specified. So in this case, this distribution cannot be used. So then we will try to the second attempt. Yeah? So we will try to the second attempt is that we lower the slope. Yeah, we lower the slope. So if initially we have higher slope like this one, because this is the result will be overshoot. So that means we have to reducing the gradient or the slope. So when we reduce the slope here, so then we can do the calculation marching from one point to another point here, and we have the value which is like this. So we have the value for two boundary conditions. The first one will be the initial condition, and the second here, the second will be the second boundary condition in which this value, which is predicted, will be undershoot or below to what we expected as in the boundary condition. So that we can try the third attempt in which we can calculate for the correct slope so that we can get the result which hit into the target. Or it means that from the marching that we've done, from the marching that we've done, we obtain the value at the boundary condition of the second boundary condition, which is at XL here, which is satisfy the value. So the result that we have satisfy the value at the boundary condition. So this is the shooting method. So we will see how it goes. How is the procedure with this? Okay, so what we do is that when we have, for example, the second order ODE, it means that we need two conditions. But when we use shooting method, it means that we only use one of the condition, which is the initial value. Now we need another initial value. So what we do is that we guess a value for the auxiliary condition. So we have to choose a guess for the second initial condition. For the second initial condition. In this case, in the previous example, we assume the slope. So the slope here is assumed. So we take one value as the slope. As we've seen before in the shooting method, we can change the angle, when we shoot it. So here the slope is assumed, and then we solve the initial value problem using Euler or other Runkuta and check if the second boundary condition are satisfied. So the result on the right side is satisfied. If it's not satisfied, it means that we have to change the value of the slope. If it's too large, it means that we have to reduce the slope. If it's too low, it means that we have to increase the slope up until we have the point, the last point, which is satisfying the second boundary condition. So this is the procedure. So this is an iterative procedure. And to make it faster, to get the solution to satisfy the boundary condition, so that we can use interpolation in updating the slope or the guess. Okay, so we will see the example here for the problem that we have before, which is the 1D heat conduction. So this is the equation. I will write it down again. Initially we have that one. TA minus T, that will be equals to 0. And then we move that to the right-hand side so that we have the second derivative of T in X. So that will be equals to heat action T minus TA. So because we have two second order ODE and we want to solve it using initial value problem, so that we have to decompose it into two first order ODE. So if we look at here, so this is actually d dx of dt dx. So the second derivative is the derivative of the first derivative. So that here, if we substitute dt dx with z, so that we have dz dx, so that will be dz dx is equals to h accent t minus ta. And the first equation is that dt over dx is equals to z. So that we have two equations to be solved. So that here, we will look again what we have learned last week. We can have two set equations, two set of ODE to find for the unknowns. So in this case, we will find for the unknown, which is the temperature. So that in this case, we have the initial temperature. We have the first value, which is at x0. The temperature, for example, is 40 degrees Celsius, on the left. And on the right, we have at x equals to L, the temperature is 200. So this is based on the boundary condition that we had before. So this first boundary condition can be used as the initial value. But we need another initial value, which is the slope. So that here we assume the slope. So the slope will be dt dx, or the z value. So here we assume that the slope at x equals to 0. So another initial value, which is at x equal to 0, we have z is equal to 10. How this value comes from, we just guess it. Take any value, use that as the slope, and then see how the result. Yeah. So that when we have that value, so that we can calculate for the margin. Yeah. So we have initial value for z, which is 10 from the guess, and this is from the boundary condition. Yeah, from the first boundary condition. So that we can do margin up to L. Yeah, up to the right side. Okay, so this is a real calculation, so that we have here the equations. We convert it into first order equations like this one. And then we guess a value for z. We take the value will be equal to 0, to 10. So then when we use the Runkuta method, in which you can read this in the book, I think this is using Yun's method. Yeah. Second order Runkuta, if I'm not mistaken. You can check that in the book. So when we use second order Runkuta method, and we have the initial guess of z, which is the slope is 10, we get the value, the temperature at x equals to L here is 168. While the boundary condition that we have, yeah, the boundary condition, the second boundary condition is that the temperature will be 200. So with the slope of 10, it means that it's undershooting the result, too low. Yeah, the result at the second boundary condition is too low. So this means that it's not satisfying. So that because it's too low, it means that we have to increase the slope. Now we take the second guess. We take the second guess, which is 20, make it larger. And then we calculate the value at the second boundary, which is at x equals to L, which is 10. So the temperature at 10 will be 285. So that means now the temperature is too high. So what we can do next is for the third guess for Z, for the slope, we can use interpolation. Yeah. So if our goal is to obtain the temperature of 200, this is our goal, finding the temperature of 200. The result here, so this is the Z value that we want. And we have the result here, which is 285, the second attempt, with using Z value of 20. Yeah, for example, this is Z, this is the temperature at X equals to L. And for Z10, for example, we have Z is 10. We have the temperature is too low, 168. So that we can do linear interpolation, such as what we do in thermodynamics, yeah, in finding the properties in thermodynamics. Yeah, so what we can do is that, yeah, we can use this correlation, yeah, so that we have 20 or Z minus 10 over 20 minus 10, that will be equals to 200 minus 168 over 285 minus 168. So that with this, we can calculate the value of Z. So Z will be 12.69. Yeah, so this will be the gradient, the correct gradient. So then we redo the calculation, yeah, with the Runkuta method, with the Hume's method. So that will be the result here. So we see the calculation, the graphs, yeah, the prediction using slope 10. We have this result, undershoot. With Z, the slope is 20, now too high, overshooting. Now if we use the interpolation, now we have Z is 12.69. We get the final result here, the most right boundary here will be satisfying the boundary condition, which is 200. Yeah. So this will be the result. So once we have this, so then we can find the distribution of each of the point inside the rod. So we know the temperature on the rod. Okay, so this is for shooting method. Any question?
Good, ma'am. Not yet, ma'am.
Okay. Okay, so this is for the shooting method, yeah? So we have to repeat the procedure. Now we will continue to the second method. Yeah. So this is the properties of the shooting method. Oh, we will see the example, another example first before we continue to the second method, in which we have another example here. Yeah. So this is also important for you to know. Yeah. Sometimes in numeric we use this symbol. Yeah. Now, if you have this symbol, don't be confused. Yeah. I think you have know that we have m dot before, for example. So that will be the first derivative. M dot is dm over dt. Yeah. The rate of mass in time. Or if we have y dot, yeah, for example, in this case, in which y is a function of x, so that will be dy over dx. And if we have y double dot, yeah, so that will be the second derivative of y in x. Yeah. So if we have this one, so this is similar to write it down as this one. Plus 2, the first derivative, plus y, and that will be equals to squared x. And we have the boundary condition, which is at x equals to 0, the y value is 0.2, and x equals to 1, the y value is 0.8. Now, we want to solve that using shooting method, so that becomes initial value problem. So we have to decompose this equation into two first order. Yeah. So if we take, for example, dy dx is, for example, z. Yeah. So if we take dy dx is z. Yeah. So that we have here. So that will be the second equation is so this equation becomes dz over dx. Yeah. Dz over dx plus 2 times dy over dx is z, so that is z. Yeah, 2 times z plus y, that will be equals to squared x. Or we can write it down here that the second equation of dz dx will be equals to squared x minus 2z. Yeah. And that will be minus y. Yeah, so this will be the second equation. So that we have two equations. It means that we have to give initial value for y and also for z. Yeah, initial for y and z, so that we can solve it. Okay, so then with the method that we have before from the Rungkutta, so that we can use that for the shooting method, and we want to determine the distribution of y here. We want to find the curve. So this is the conversion, yeah, in which this will be another problem. So this is not the same, yeah. Is this the same? Oh, this is not the same problem. Yeah, different problem. Okay, so then if we have this one, so that we can convert it into two equations. So in this case, we have d squared y over dx squared. That will be equals to 4, move that to the right, 4y, 4 positive y minus x. Yeah. And here we use y1 and y2 here. So y1 is actually the y value, and y2 here will be the z value. Yeah. So if we have it here, so that we will have, we have d y over dx, for example, that will be z. Yeah. So that we will have the second equation will be del z over dx. Yeah. That will be equals to 4y minus x. So we have two equations. So this is the first equation and this is the second. Now if we have z is y2, so that we have, so y1 here is y, and z y2 here is z. Yeah. So that if we have dy dx, so y here is y, y1. So that will be y1 dot, that will be equals to z, which is y2. And we have y2 dot, which is dz over dx, y2 dot, that will be equal to 4 times y, which is y1 minus x. Okay, so that we have the first boundary condition, we have the initial condition for y1, which is the actual value of y, which is 0. Now we don't have the slope here, z value or the slope, we don't have it. So we make an initial guess. So this is what we do. Take any value for the guess. And here we choose the easiest, which is 0. So when we use the initial guess of the slope is 0, like this one, so then we can calculate the value at 1 here will be minus 0.7688. While the actual value should be 2. So at x1, y should be 2. So we see here that this is very low, below the boundary condition. So that we can try the next guess, make the slope larger, so that now we choose 1. When we choose the slope is 1 here, so then now we have the calculation like this one, and we have, this is still also undershoot. So the actual value for the boundary condition should be at 2. Should be at 2. But here we have the value is still 0.99 with the second case. So what we can do extrapolation. So this is interpolation, but outside the range of the data that available. So this is also called interpolation. So in English, it's also called interpolation, although this is actually what we call as extrapolation. So that we have here the value when we use y or y dot, or we have the slope here is taken at 0, we have the value at the boundary, the second boundary will be 0 minus 0.76. When we choose 1, we use 0.99. So that we can also extrapolate here to get the value of 2. Our goal is to get the value in which the second boundary is at 2. So that here, when we do extrapolation as well, so that will be at 2. Here we have the slope should be 1.57. So then when we use this slope in the calculation, so that we will have this finally satisfying the second boundary condition. So this will be the result for the distribution. So this is the solution to the boundary value problem. Okay. So this will be the shooting method. And we see in the procedure. Now we will continue to the second method, which is the finite difference method. So this will be quite short because you have learned this in heat transfer as well. So what we do in the finite difference method is that we substitute, we substitute it. So we substitute the derivative that appears in the ODE with the numerical differentiations that we have before. Now again, recall in numerical differentiation, we can have forward scheme, backward scheme, or central difference scheme. Now in this case, we will use central divided difference. So we use central divided difference to substitute for the derivative in the ODE. So that once we substitute it with central divided difference, so that the PDE will transform into a set of linear algebra equations. And once we have that, so that we can solve it using any method that we have before. For example, we have Gaussian elimination, we have, for example, Gauss-Seidel or other methods. So we can use that to solve for the solution. Okay, so we will see here. Again, central divided difference. Remember, when we learn about numerical differentiation, we can find the first derivative, second derivative, up to third and fourth derivative. So if, for example, we have ODE in which it contains fourth derivative, so we can easily solve it by only substituting the central difference scheme here into the equation. So it's very easy when you use finite difference method. Okay, so back again to our example, which is about heat conduction, 1D heat conduction, in which here we have this equation. So what we do here is that when we have a derivative, so that we will substitute that with central divided difference. In this case, this is second derivative, so we will substitute that with the second derivative as this one. So that the second derivative will be ti plus 1 minus 2 times ti plus ti minus 1, and that will be divided by delta x squared. Yeah. So that when we substitute this one into the equation, so we will have this equation. Yeah. So this is a linear algebra equation, a linear equation. Yeah. Linear equations. Why? We don't have the derivative anymore. And this is all first order, yeah, linear power 1. So this is a linear equation. Yeah, so when we have T here, so that directly becomes Ti at the temperature at that point. Okay, so once we have this equation, so that we can do discretization, yeah, so we can divide the length, for example, into points, yeah, into points. So that will be final difference. So that we will collect the term together here. We have Ti, we collect together. We have Ti, and Ti, we collect together. We have Ti plus 1, and we have Ti minus 1, and all the constant can be moved to the right-hand side. Yeah. So this will be here. This will be it. Yeah. So we have Ti minus 1, we have Ti, we collect together the coefficient, and we have Ti plus 1. And all of the value, the constant value, will be the right-hand side. So again, when we have this one, we can apply to the interior point of the domain, so that what we have will be a11x1 plus a12x2 plus a13x3. So that will be P, or back again to what we remember when we solve about set of linear algebra equations, so that we have matrix coefficient matrix A times the factor of the unknown factor X, that will be the right hand side P. So the unknown here will be the temperature here. The right hand side here will be all the constant value, which is usually obtained from the boundary condition as well. Yeah. Okay. So we will see that this equation now will be applied to the interior point, and the first point and the last point will be the boundary condition. So that will be a total of 5 points. So if there is a total of 5 points, it means that we have 3 interior points, or we have 3 unknowns. It means that we have 3 equations as well. So 3 equations to solve 3 unknowns. Okay. So we will see here the explanation. Say we have the example, yeah, we will see an example, slightly different example here. We have second order ODE. Now we have the second derivative, so that we can substitute it with this second derivative. So that will be yi plus 1 minus 2yi plus yi minus 1 over square delta x. So we substitute it here. And we have minus 2 dy over dx, in which dy over dx here will be yi plus 1 minus yi minus 1 over 2 times delta x. So this is for the first derivative using central difference. So both of these are central difference approach. Minus y plus x, that will be equals to 0. So that when we insert this value, so we will have a linear equation. And we have 2 boundary conditions here is specified, and delta x is also specified. So that here we can substitute it, collect together the terms. We have yi plus 1, we collect together. We have yi minus 1, we collect together, so that we have the coefficient here. And also yi, we collect together, okay, and xi. So that if we have from 0 up to 10, and we have delta x is 2, yeah, so that we have, for example, from 0 to 10, so that with delta x2 we have 0, 2, 4, 6, and 8. Yeah, so it means that we have 1, 2, 3, 4, 5, 6 points, including the boundary condition. Now we have the boundary condition is specified at x0, so this will be the boundary condition, and x at 10. So that the interior nodes means that we have 1, 2, 3, 4. So 4 interior nodes. So for each of the node, we will apply this equation. Yeah. So for example, if we want to find y at 2, so that will be calculated from y at 4 minus 1.5y at 4 on the right side, yi plus 1, the right side, minus 5 times y at 2, plus 2.5 yi minus 1, the point at 0, plus xi, that will be equals to 0. And we can also apply the same for the other points. So this will be the equations. Yeah. So if we have an index of 0 up to 5 for all of the points, so we have 4 interior nodes. So this will be the 4 interior nodes, which is at 2, 4, 6, and 8. So this is the corresponding equation. If we have the boundary condition here, we can insert that as well here. We have y5, so that we can insert it in the equation here. So that this value should move to the right-hand side. Yeah. So the constant value later will move to the right-hand side. So that we can form the matrix in which we have here the coefficient of the point itself, or I, the coefficient of I plus 1, and the coefficient of I minus 1. So we have a banded matrix here. Yeah. So we have a case of a banded matrix. So you will see here that when we have a banded matrix, it typically arise from the finite difference problem. Yeah. And we have the unknown here, and this will be the right-hand side. So that when we have this matrix constructed, so you can use Gaussian elimination, for example. Yeah. Or if we have the right-hand side changing by time, so that we can use, for example, LU decomposition, or even iteration method, such as Gauss-Seidel. So you can see that there is a correlation between what we have learned previously to what we are aiming to. Yeah. So when we learn about ODE, we talk about more complex equation. This is really relates to engineering problem. Yeah. We commonly found partial differential equations and also ordinary differential equation in mechanical engineering. So how to solve this? So you can see the big picture now. So what we do is that we do discretization, and then we can apply the solution for set of linear algebra as what we have learned before. Okay, so I think that will be all for today. Yeah, any questions?
Maybe review lagi mungkin tanya minggu depan.
Ya, kenapa?
Mungkin masih belum, Mem. Okay. Nanti pas ada problem-problem gitu mungkin besok bakal ditanyain.
Okay, yeah. Okay, so yeah, because I think you have learned about this as well, yeah, in heat transfer, yeah, is that correct?
Yes, ma'am.
Okay, so when you learn in heat transfer, if I'm not mistaken, that is using Gauss-Seidel for the solution. Yeah, so it's using iterative method in which, basically it's using Gauss-Seidel to solve the set of linear algebra equations. So that will be one of the example. Yeah. Okay, so yeah, before I close this class, there is a little bit more here which is relates to the MATLAB. Yeah, so that for the solution for the ordinary differential equation, particularly this is for the initial value problem. So we can use a special function in MATLAB. Yeah, so there is a built-in function in MATLAB in which we can find the solution by calling the name, yeah, of the function. So here we can see that if we have an equations, for example, we have two equations, two ODE, in which this is initial value problem. So we have the value of x and y at t equals to 0. So it means that we have two condition, two value at the same initial time. Yeah. So this is initial value problem. So that when we want to solve this in MATLAB, you can do that. First, we have to insert or defining the equation that we have. So we see here that we have a function of yp. We give the name for this would be the name of bread tray, for example. You can give any name. So this is the name. So that will be inserting two equations that we want to solve. So this is the first equation, which is 1.2x in which x here is defined as an array, which is this x will be the first element in the array. So that will be y1 minus 0.6 x, which is y1, times y, which is the second element in the array. And we have also the second equation in which we have here minus 0.8 times y2 plus 0.3 times y1 times y2. Yeah, so we have defined the function here. Now, how to solve that in MATLAB? We have a built-in function which is called ODE23. Yeah, so this will be the second order Runkuta. Yeah, ODE23. So that when we want to plot the graph, we should define the x value or the t value in this case, the abscissa. Yeah, the abscissa is t. So that we have to define the abscissa will be a span. There will be a span for the abscissa which is from 0 up to 20. And this will be the initial condition. So y0 is the initial condition, which is the initial condition for y1, which is the x value, will be 2. And the initial condition for y2, which is y, is 1. So that we can call the function, call the function which is ODE23, and we put that in a matrix which is ty. Yeah, so that will be equals to ODE23. We call the function which is Bradbury, comma the c-span, the abscissa value that we want to generate from 0 to 20, and the initial value. Yeah. So this is the argument that is passed using function ODE23. Yeah. So how to see for the argument that is passed? You can look at the MATLAB manual help. Yeah, or the documentation of MATLAB. Yeah. So that when we put in the function, the span, and also the initial value, and then we plot it, so that we will have the result here. So in this case, we have two graphs in which these two graphs first represents the first equations of the ODE, and the second is the second equation here. So this will be the equation for x, yeah, starting from initial value of 2. So this is the graph, and this will be the second equation of the ODE. Okay. So this is how to directly solve it in MATLAB, yeah, in which what MATLAB do is actually applying what we have learned. Yeah. So MATLAB is putting the algorithm inside. Yeah. So built as a built-in function. Right. So that is for solving initial value problem using MATLAB. Yeah, so I think that will be all for today. Yeah, so we will continue again next week, inshallah. Yeah, on the calculations of on the solution of PDE, yeah, partial differential equations. Now, before that, I want you to work on the problem, yeah, on the problem that we have before, which is on the slide, the previous slide, yeah. So that will be on lecture note week 13, which is about the ODE using solve the ODE using analytical solution, yeah, and then using Yun's method, midpoint method, and fourth order Runkuta. Yeah, and then you need to also plot the graph. Yeah, so when you do that, it means that you have to do that manually, not using MATLAB. Yeah, but later, if you want to plot the graph, you can use MATLAB or Excel. Yeah, but for the calculation, you need to do it by hand. Yeah, okay. Okay, so that will be the assignment due next week. Yeah, assignment due next week before the class started. Okay, so next week class we'll back again. Hopefully we can start at 9:45. Okay, so that will be the end. Any question?
No, ma'am. There.
Okay, okay. So thank you. Wassalamualaikum warahmatullahi wabarakatuh.